In this video, we will be doing section 3.7, and it is curve sketching a summary. Alright, so you can read sort of why we do curve sketching in this short paragraph that is on this page here, but essentially a lot of things can be done by computer or by calculator now. But the calculator or computer doesn't necessarily give you all of the details, like if there's a hole in the graph, or an asymptote, or any curves in the graph. The calculator might not give you, again, as much detail. And so there is a lot of still good reason why we would want to draw the graph by hand. Alright, so here are the guidelines for analyzing the graph of a function or drawing it by hand. Determine the domain and the range. Determine the intercepts and asymptotes of the graph. Locate the x values at which the first derivative and second derivative are 0 or undefined, meaning the critical values of the first and the second derivative. And then use those results to determine where the relative extrema and points of inflection occur. Alright, so topic 1, summary of curve sketching techniques. Analyze the graph of each of the following functions, and then sketch the graph, making sure to label any intercepts, relative extrema, points of inflection, and that's it, points of inflection. Who did that? Was that you, Jonathan? Alright, points of inflection. That should say points of inflection. Alright, sorry about that typo there. And asymptotes. Alright, so let's first find the x and the y intercept. Alright, so here I'm going to draw this right here. So the x-intercept occurs when y is 0. So 0 is equal to x to the third minus x squared minus x plus 1. Now I can factor that. Factor out an x squared from the first two terms, so x squared, x minus 1, and then a negative 1 from the second two terms, so that's x minus 1. So that is going to be x squared minus 1 times x minus 1, then factor the difference of squares, which is x plus 1, x minus 1 times x minus 1. Excuse me. Okay. So now I set each of these factors equal to 0, so x is negative 1, or x is 1. So that means there's x-intercepts at negative 1 and at 1. Alright, now let's find the y-intercept. That's when we set x equals to 0, so we just need to find what y is, so that's 1, so the y-intercept is at y equals 1, so that is right here. Now we just need to find the derivatives to give us an idea of what's happening between these points. So let's find the first derivative. It is 3x squared minus 2x minus 1. Alright, so now what you need to do is actually graph that and find the zeros of it. So let's bring the calculator up on the screen. And, oh boy, I just tried to run it. Here we go. Alright, so let's bring the calculator up on the screen. Where is it? Come out of hiding. Alright, so I'm going to turn this on. Alright, so turn it on. And go to 3x squared minus 2x minus 1 and graph that. Alright, now I'm going to find the intercepts, so the zeros. So if I move this to the left a little bit and hit enter, and move it to the right a little bit and hit enter, then I see that one of the values is actually x is equal to negative a third. And then let's go and find the other intercept. So calculate 0, go over, enter again. So my guess that it is at 1. Alright, so now that is sort of a sketch of what this looks like here. So here is negative a third, here is 1, and you saw that the graph opened up. So that means on this interval, the first derivative is actually positive. So the f of x is going to be increasing, and then it goes to decreasing because the derivative is negative, then back to increasing because the derivative is positive. That means that at x equals negative a third, we're going to have remember, going from an increasing to decreasing is a relative maximum, and from a decreasing to increasing is a relative minimum. Alright, so we're going to, relative minimum. We're going to put x equals negative a third and 1 right on the graph. Alright, now we need to find f of negative a third. So that is negative a third to the third minus negative a third squared minus negative a third plus 1. So I'll give you a second to do that. Actually, let's see if I have it stored in my calculator already. I'm not sure if I do or not, so I might have to retype it myself. So this will give you a second to do that as well. But this happens to be about 1.2. Alright, so here it is. Alright, negative a third, 1.2 is right about there. And then we already have f of 1, which we said earlier was 0. It's right here. So this is going to be my relative maximum. And that's going to be my relative minimum. Now I need to find the second derivative. So it is actually 6x minus 2, which is just a line, so that one's a little bit easier to graph. It has an intercept of negative 2, and then if I set this equal to 0, I see that the intercept is actually at 2 over 6, or a third. So this is going up 6 over 1 because of the slope of 6. So it just looks something like this. And again, this point is a third. So remember what the second derivative does. When the second derivative is negative, that means that the graph is concave down. And when the second derivative is positive, that means the graph is going to be concave up. So that means that 1/3 is a point of inflection. So let's draw that on here. And then we need to find f of 1/3. So I'm going to just tell you what that happens to be. And it's about 0.6. So I'm rounding a lot here just to make sure that it's easier to graph these. So it's at 1/3 and then 0.6. And then you just connect the points. So it goes up and that back down for concave down, and then down and then back up for concave up. Alright, so this point right here is my point of inflection. I hope that all of you are enjoying this. Alright, oh, I should have said pints of inflections. Alright, there you go. There's your point of inflection. Alright, well, I hope that, again, you will ask any questions if you happen to have any. please don't hesitate to ask ever. But I have great news. It is now time to move on to problem B. Alright, x squared minus 9 over x. So let's first find the intercepts. So I'm going to graph this right here. Alright, so we're going to have to figure out how to do this one. I don't think it's going to be as bad as you might actually think. I mean, it's going to be bad. I'm not going to lie about that, but it's not going to be as bad as you think. So let's find the y-intercept. So that's setting x equal to 0. Can we have x equal to 0? No, that is undefined. And actually, since x cannot be 0 at all, we're actually going to say that x equals 0 is a vertical asymptote. Now, if that weren't exciting enough, we're going to say, well, there are no y-intercepts, and try to find the x-intercepts. So let's let y equal 0. So 0 is equal to x squared minus 9 over x. So we really just need to set the numerator equal to 0, and then factor using the difference of two squares. So then we have x plus 3 is 0, and x minus 3 is 0. And we subtract the 3 and add the 3. So x is negative 3 or 3. Those are the intercepts. I hope that you're enjoying this, Jonathan. I truly am. And Maxine, I hope you're enjoying this as well. Alright, so now let's find the first derivative. So we'll need to use the quotient rule. The bottom, x times the derivative of the top, 2x, minus the top, which is x squared minus 9, times the derivative of the bottom, which is 1, all over this bottom part, x squared. I'll actually make that parentheses a little bit more clear here. Uh-oh. Alright, now let's simplify that. That's 2x squared minus x squared. Distribute this negative, so that's plus 9 all over x squared. So I have 2x squared minus x squared is x squared plus 9 over x squared. Alright, so now I sort of need to draw a sketch of this. And so let's bring up the calculator so that you can see where I'm getting this from. I don't know why this keeps on going over there. The struggle is real for me with this calculator here. Okay, I am just gonna, well, now you can't see it. Okay, now I'm just gonna turn it on and leave it over here. Alright, let's go to y equal and clear that out. And then try to, well, okay, this one is not updated. Oh, bah humbug, right? So let's type it in. X squared plus 9 divided by x squared. And then graph this. So we need to see if there are any intercepts. And there are not. If I look carefully at what was going on, the graph sort of looked like this. And so everywhere I looked, I noticed that the first derivative is always positive. Always positive. So since the first derivative is always positive, that means that the graph of f of x is always increasing, which means that there are no relative extrema. Alright, now let's find the second derivative, f double prime of x. It's the bottom, x squared times the derivative of the top, 2x minus the top, x squared plus 9 times the derivative of the bottom, 2x all over x squared squared. Alright, I hope that all of you are truly enjoying this. I care about all of you so much. Alright, so x squared times 2x is 2x to the third. Let's distribute this. Don't forget the negative as well. So that's actually negative 2x to the third. And then, what is it? Minus 18x all over x to the fourth. Alright, so cancel those. So it's minus 18x over x to the fourth, and cancel that. So it's minus 18 over x to the third. Alright, so since this is another one that might be a little bit difficult to graph, let's use the calculator again. So let's go up here, y equals, and we have negative 18 over x to the third. And let's graph this. And you can see what is going on here. Alright, this is up here. And this looks to be down here, sort of like this. Alright, so all we know from this graph is that when the second derivative is positive, f is going to be concave up, and this is going to be concave down. Now, there is no point of inflection because the function and its derivatives were both undefined at 0. So again, remember, we already knew there was an asymptote right here. So all this means is that on the left here at negative 3, the graph is going to be increasing, but concave up. And then on the right side, the graph is going to be increasing, but concave down. Alright, so what is that going to look like? It's going to look something exactly like this beautiful graph I'm about to draw for you. So it's increasing and concave up. And this one is increasing, but sort of pointing in a downward direction like this. Kaboom! The struggle is no longer real. Alright, by the way, another thing that you could have done for this problem is actually found the slant asymptote if you wanted to, but I really don't think that we need to do that. I didn't actually show you specifically how to do that, but it is in your notes. Alright, so let's look at C. X times the square root of 9 minus x. Alright, so let's first find the y-intercept by setting x equals 0. So that would be f of 0 is 0 times the square root of 9 minus 0, which is 0. So we have an intercept at 0, 0. Now we need to find the x-intercept and set y equals 0. 0 is equal to x square root of 9 minus x. So this one is one of those funny ones where technically you could just say each factor is 0. So either that's 0 or square root of 9 minus x is 0, square each side, and then subtract the 9 and divide by negative 1, so x is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 is another intercept. And now we need to find the Derivatives. That sounds like a TV show. It's like a game show. We just need to find them. Alright, so let's find f prime of x. So I'm going to write the f of x is x times 9 minus x to the 1/2. So I actually have the product rule, the first times the derivative of the second one. So remember to use the chain rule here, then plus the derivative of the first times the second one here. So if I simplify this, this is negative x over 2 times 9 minus x to the 1/2 plus 9 minus x to the 1/2. Alright, so I'm just going to actually go ahead and enter that all right in the calculator because it would take longer to simplify it than it's worth. So, negative x over 2 times 9 minus x to the 1/2 power, and then plus the 9 minus x to the 1/2 power. Alright, Nicole, are you enjoying this? I thought that you might be. Alright, so let's graph this. And if I look very carefully, I can sort of see where the critical numbers are. Alright, so let's calculate the 0 here. Move this closer to 0. Oof, this is a lot of work. Okay, enter. And then over here, enter. And I get 6. Alright, so this is sort of what this graph of the derivative looks like. It looks like there's an intercept at 3 and at 6. Whoops, I'm not going to put that little arrow there. And that the graph sort of looks like this. Uh-oh, not like that. Don't draw that. Draw something nicer. Kaboom! Alright, and then it keeps on going down like that. So, that means since the derivative is going from, actually, positive to negative, that at x equals 6, we have a relative maximum. Alright, so 1, 2, 3, 4, 5, 6. Now we have to find f of 6. And remember what the original function is. It was 6 times the square root of 9 minus 6. So that's 6 times the square root of 3. And as a decimal, that is about 10.4. So 6 10.4 is our relative maximum. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.4, and then 6. Where is it? 1, 2, 3, 4, 5, 6, right here. Alright, so that is our relative maximum. Now we need to see if there are any points of inflection. And to do that, we need to find the second derivative. Alright, so I truly hope that all of you are enjoying this. Alright, so we need to find f double prime of x. So, this is going to be a very awful one, but we have to use the quotient rule. So we have the bottom 2, 9 minus x to the 1/2 times the derivative of the top minus 1 minus the top negative x times the derivative of the bottom 2 times a 1/2 times 9 minus x to the negative 1/2 times the chain rule of a -1 all over the bottom squared to 9 minus x to the half all squared, and then plus the derivative of this guy right here, which is a half times 9 minus x to the half time, to the negative a half times the chain rule of a -1. So, I'm just going to go and put that in my calculator right now, because I know that this is actually a lot of work for you to all do. Alright, so I appreciate all of your enthusiasm. Right? The enthusiasm is real. At least I'm hoping it is. Alright. Whoops. All over 2 times 9 minus x. I'm still putting it in my calculator. And I just feel like, one of the things that I want to do is make sure that I give you enough of a chance to try to do this on your own as well. Alright. Woof. Well, alright, so what does the second derivative look like? Oh, let me draw a sketch of that down here. Alright, so again, this is going to be something that I think is just, in my opinion, sort of dead awful to do. Whoops. I just realized that you guys couldn't see the calculator. Alright, so I couldn't get that to show up, so I just got rid of it. But this is sort of what the graph of the second derivative looks like. So we still have it looking like this. But it is actually negative everywhere. So since the second derivative is negative everywhere, that means that f of x is concave down. So all we have to do now is draw something that appears to be concave down. Now, by the way, I cannot go past this 9 here because of the domain. 9 minus x has to be greater than or equal to 0. Subtract the 9, divide by -1, and flip the sign, so x has to be less than or equal to -9, or else we would get a negative under the square root. Kaboom! Alright, now we are fresh out of time for C, but I think we have some time in the schedule for D. Alright, D is kind of exciting. We can find the y-intercept by setting x equal to 0. So 0 minus 3 over 0 is undefined. So again, this is a very similar situation to the ones that we may have seen before. We have an asymptote at x equals 0. Then we have the x-intercept when y is equal to 0. So 0 is equal to x minus 3 over x. So set the numerator equal to 0 and add the 3. So x is 3 is an intercept. Now we need to find the first derivative. So we have the quotient rule, the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom part squared. Alright, so now I'm going to actually simplify this. X minus x plus 3 over x squared, or just 3 over x squared. Now, 3 over x squared is one that I think is common in everyday life. I mean, at least I think it is, Maxine. Alright, so let's graph this. Here it is. you can use a calculator to graph it. But would you agree with me again that this derivative is positive everywhere? So that means f is always increasing, and it is no relative extrema. Alright, now we need to find the second derivative. And if this is the first derivative, that's 3x to the negative 2. So this is just negative 6x to the negative 3, or negative 6 over x to the third. That means that if you graph this guy, negative 6 over x to the third, on your handy, not so dandy, necessarily, graphing calculator. Oh boy, my calculator is broken. Alright, so here is what this looks like. This reminds me of the other one that we did, right? Okay, so we see over here that f is going to be concave up because the second derivative here is positive, and concave down over here because it is negative. Alright, so now we just need to get ready to graph the final answer. Now, we know that another thing is that the horizontal asymptote is the ratio of these, which is going to be x over x, which is 1, so y is 1. So 1, 2, 3, 4, 5, 6, 7, 8, alright, dashes across. Now, it has to go through the intercept here of 3, and it needs to be increasing and concave down. So it looks like this. And then over here, this needs to be increasing and concave up. Kaboom! This has been real. Alright, again, if you have any questions, please feel free to ask. But let's just do a quick summary now. So we want to sketch a curve with the following properties. So the first derivative is greater than 0, meaning increasing, increasing, and then if the first derivative is less than 0, decreasing, and if the second derivative is positive, concave up, negative down, positive up, and negative down. Alright. Alright, so now let's just follow the restrictions on x and do this. Now, if f is going from increasing to decreasing, that means that there is a relative maximum at this point. And when it's going from concave up to concave down, that means an inflection point. So point of inflection, and from down to up, point of inflection, and from up back to down, a point of inflection. Alright. So for x less than negative 1, here's negative 1, we're increasing and concave up. So something like this. Now at 1, I have to be increasing but concave down. So I have to, but it cannot be a relative maximum. So I have to keep on increasing but go concave down. Uh-oh. I was trying to remove the axis because I drew the arrow way too large for you guys to see that. Okay, concave down. But then at 0, I see I have a relative maximum. So it's going to start going back down. So decreasing and concave down. So going back down. But then at 6, 1, 2, 3, 4, 5, 6, I have, it is decreasing, and, 0 to 6, decreasing concave down. And then at 6 to 8, it will be decreasing but concave up, so still going down but starting to point back up. And then for greater than 8, which is over here, and again this arrow got in my way, so I'm just going to draw this back over here. Okay, so for what is that? 1, 2, 3, 4, 5, 6, 7. Okay, for 8, decreasing but concave up, so meaning that it is going back up. And then from 8 on, it's decreasing but concave down, so pointing back down. Alright, so here was my point of inflection. Here was my relative maximum. Here was my other point of inflection. And here was a point of inflection. I hope that you guys have found this enjoyable, because I've enjoyed telling you about this. Alright, last page here. Y equals 3 is an example of a constant function. Sketch the function and name its degree. So it is a horizontal line at 3. So the degree of this is 0. Alright, 2x plus 5 is an example of a linear function. Sketch it and name its degree. Alright, so I know that it has a slope of 2 and a y-intercept of 5. So I'm going up to right 1 and drawing this. And this is a degree 1 function. Alright, the first power. Alright, now let's look at C. Here's a quadratic function. So again, I would just use the calculator if it said sketch, except my calculator is not working right now. Alright, so here we have a sketch, and it just really is in all honesty, like a basic sketch. Alright, it's just going to do something like that. And what is the degree? It is degree 2. Alright, next one. We have 3x to the third minus 5x squared. 3x to the third minus 5x squared plus 2x minus 1. And what degree is that? It is degree 3. And it should look like your normal cubic function. Something that is going down and back up. Some S-shaped curve. Again, my sketches really are sketches. Alright, and then let's look at E. How many points of inflection does a quadratic function have? And that would be 0, because it's either concave up or concave down all the time. But a cubic function has 1 point of inflection. Alright, well, I have great news, Jonathan. We are done. So, I hope that all of you enjoyed this video.